This video covers Chapter 1, Part 3, Sections 10 through 12. The learning objectives that we will cover include using the factor label method, dimensional analysis, to solve problems, defining the relationship between temperature and heat, and converting temperature units, defining and converting units for measurements of heat, use the temperature and specific heats to determine the flow of energy and matter, and to define density and specific gravity, and use these quantities to calculate mass and volume. So we'll take a look at the first objective, use the factor label method, dimensional analysis, to solve a problem and to check the result to make sure that is correct. When we're doing calculations in chemistry, a number of calculations are going to include using the conversion factor. And we've looked at conversions before when we looked at prefixes for metric units, and we had to convert between different metric units. Here we can use conversions of equalities to help us calculate different values. So you can use equalities such as 1 mile is equal to 0.6214, 1 kilometer is equal to 0.6214 miles, or 0.6214 miles is equal to 1 kilometer in doing conversion factors, because they are all equal to 1. A number divided by itself is equal to 1. So that's why we can use them in mathematical expressions. You can click on these links to videos in this PowerPoint that you have posted on Blackboard to help you practice these types of calculations. You may have thought of some other equalities that you might use on a daily basis. What may some of them be? Well, when you go to the store, you buy how many eggs? Right, a dozen. So it's 12 eggs in 1 dozen. We will talk about another conversion later on in the semester called the mole, and it helps us to describe really large quantities of usually small things. So when we use unit conversions, we can use them, we treat them like numbers, and they can be multiplied and divided. And we noticed before that we can flip them around depending on what we need to find. So when we want to use a conversion, first you set up the equation so that all the unwanted units cancel out. And you're going to always start with the amount that's given in your question. So how many kilometers are in 26.22 miles? Well, you start out writing down what you're looking for, and then you begin your calculation with the starting quantity, which is 26.22 miles. You set up your conversion factor so that kilometers is on top and miles is on the bottom, so we can cancel them out in the calculation, and we're left with kilometers as our units in the answer. And we notice here that we have 4 significant figures in our starting amount, and we have 4 significant figures in our final quantity. Here are some common equalities. We have some metric and US equalities and metric versus US equalities. The ones that you should definitely know, oh, you know what, I didn't include these as well, but you should know these different prefixes for these quantities, and you should know these different conversions just because these are metric conversions. Here for the US to metric conversions, you should know an inch to a centimeter, kilograms to a pound, grams to a pound. Other ones will be given to you in your questions, like on exams. These are typical units that are used in nursing. Notice that in milliliter we have cc's, and for milligrams we have mcg's. For micrograms. For milligrams, this does not, I want to say that should be microgram, but I'll have to check that out. Let me check that and I'll get back to you in a Blackboard note. But I did use this equality as micrograms later. Let's see. When we're solving a problem, you want to do 3 things before you start your problem. So when you're reading a question, you want to do something before you just start to go answer the question. You want to first identify your given information and the units that are involved in what's given. You want to find out what information do you need in your answer, and you need to know what units your answer should be in, just in case you have to do some converting with metric prefixes. Also, you need to find out what are the conversion factors that you need to solve the problem, and then you make a plan. You take a look at your answer to determine whether it makes sense. And if not, you start over again. So let's write the conversion factors for the following pairs of units. We want to go from from pounds to grams, and from deciliters to milliliters. Let's take a look at A first. Well, here we would have to check the table, and if we go back a couple of slides and take a look at the table, we'll see that 1 pound is 454 grams, or 454 grams is 1 pound. This is one of the ones that you should commit to memory. To determine how many milliliters are in deciliters, you have to do a little bit of dimensional analysis using conversion units. So first, we know that deciliters are going to be 0.1 liters. And we know that 1 milliliter is 0.001 liter, or 10 to the minus 3 liters. So we can figure out what the conversion is between deciliters and milliliters by doing a calculation. So 1 deciliter is equal to 0.1 liters times 1 milliliter per 0.001 liters, and we end up with 100 milliliters. So now we have an equality of 1 deciliter is equal to 100 milliliters, and now we can write our conversion factors. 1 deciliter to 100 milliliters, or 100 milliliters to 1 deciliter. If you remember in lecture, we discussed a short version where we can use a number line and count the spaces between the units. If we were to look at the number line, 1 deciliter is 10 to the minus 1, whereas a milliliter is 10 to the minus 3. There are 2 decimal places between deciliters and milliliters, and so those 2 decimal places relate to 10 to the 2. So knowing that milliliters are smaller than deciliters, we would have to have more milliliters than deciliters. So it takes many more milliliters to make up 1 deciliter. We could also write this conversion factor as 1 milliliter over 10 to the minus 2 milliliters. That can be written as 1 milliliter is equal to 10 to the minus 2 deciliters. 1 milliliter is equal to 10 to the minus 2 deciliters. Let's try another problem. First, remember you need to figure out what is the given information. So you read the question. A child is 21.5 inches long at birth. How long is this in centimeters? Well, identify the given information as 21.5 inches. It's a length. Then we identify the answer in units. We need to know how long is this in centimeters. Next, we need to identify a conversion factor. Well, if we remember a little while ago, we said that 1 inch is equal to 2.54 centimeters. You set up your problem and you solve. 21.5 inches times, notice that we put centimeters on top and inches on the bottom so that inches can cancel out, and we're left with 54.6 centimeters. Notice that we have 3 significant figures in our answer. How about you try these problems on your own? Remember, you have to first figure out what is given and what you need to know, and then determine what your conversion factor might be. Go ahead and think about what is given and what you need to know for number 1. If Greg weighs 144 pounds, what is his body mass in kilograms? Okay, so we know what's given is 144 pounds and that we need to find the mass in kilograms. So we also know that our conversion factor is 2.2 pounds is equal to 1 kilograms. We set up our problem starting with what we're given. Then we multiply by our conversion. Notice that we put kilograms on top and pounds on the bottom so that our answer we get is in kilograms. If we put this in the calculator, this is a shortened version of our answer, but how many significant figures do we need to have to make this answer correct? Correct, 3 sig figs. Let's look at the second problem. Synthroid is used as a replacement or supplement therapy for diminished thyroid function. A doctor's order prescribes a dosage of 0.15 milligrams of Synthroid. If tablets in stock contain 75 micrograms of Synthroid, how many tablets are required to provide the prescribed medication? Well, what's given? We know what's given is 0.15 milligrams of Synthroid. We also know what's given is that we need to know how many tablets there are, and our stock contains 75 micrograms of Synthroid per tablet. Well, we need to know the number of tablets. If we know that 0.51 milligrams is equal to, we know that we're starting with 0.15 milligrams, and we multiply 1 tab by 75 micrograms, and 10 to the 3 micrograms is equal to 1 milligram. We cancel everything out, and we end up with 2 tablets. Next, let's try this problem. Go ahead and figure out what's given, what you need, and what are the conversion units you need for this problem. It's a little tricky. You might have to do a little bit of conversion before you begin. Okay. Well, we know that we have 120 milliliters of cough syrup. The problem reads, a bottle contains 100 milliliters of cough syrup. If 1 teaspoon, 5 milliliters, is given 4 times a day, how many days will elapse before a refill is needed? We need to know how many days before we finish the cough syrup. Well, our conversion is given here. There's 5 milliliters that are given 4 times a day. However, we need to know how many days. So we know that there are 120 milliliters in the bottle, and yet we give 5 milliliters 4 times a day. So that equals 20 milliliters a day that we use out of the bottle. So we're going to use this conversion to figure out the number of days. You go ahead and set up the problem, and I'll follow along behind you. Okay, always start with what you're given, 120 milliliters. Then you use your conversion factor. Notice that we have our days on top and milliliters on the bottom so that we can cancel those out, and we equal 6 days. Let's try another problem. A patient is to receive 16 milligrams of methimazole, a drug used to treat hyperthyroid conditions. The drug is dissolved in a solution containing 8.0 milligrams per ml. What volume of solution should be administered? Go ahead and figure out what's given, what you need to answer with, and what are your conversion units. Okay, now let's write everything down. We have 16 milligrams of the drug, and we need to know what volume of the solution that's going to provide 16 milligrams. The solution contains 8 milligrams per ml. So we know we're given 16 milligrams, and our conversion unit is 8 milligrams per ml, and we need to know the milliliters of solution. 16 milligrams, we start with what we're given, times 1 milliliter per 8 milligrams. Notice that we switched the conversion unit upside down so that milliliters are on top, milligrams are on the bottom. And what's your answer? 2 milliliters. All right, why don't you try this problem on your own? You can pause the video if you need more time to finish your calculations. The answer is 10 milliliters. Well, we know that 500 milligrams is given. We need to know the number of milliliters. Our solution is 250 milligrams per ml. So, in order to find out the number of milliliters of antibiotic we start off with 500 milligrams times 5 milliliters per 250 milligrams. Put that in your calculator, and with the correct number of sig figs, you get 10 milliliters. Now we'll talk about temperature, heat, and energy. All chemical reactions and a lot of physical reactions are going to be involving a change in energy. So how do we measure energy, and how do we know whether something is gaining or losing energy? So the learning objectives for this section and chapter is define relationships between temperature and heat and energy, and convert the temperature between various temperature scales. Define and convert between units of heat measurements, and use temperature and specific heats to evaluate the flow of heat or energy in matter. So if you remember what the definition of energy is from way back when, is the capacity to do work or to supply heat. Temperature now is a measure of the amount of heat or energy in the object. And if we think about it, heat is due to what kind of energy? Kinetic energy. If an object has an increasing amount of kinetic energy, then it has more and more heat, and its temperature will be higher and higher. You can watch these videos to help you understand energy and temperature scales and to practice doing temperature conversions. Kelvin and Celsius scales are similar in that 1 degree Celsius is equal to a change of 1 Kelvin degree. So when we are looking at the Kelvin scale, it is an absolute scale. And on absolute zero is actually negative 273.15 degrees Celsius. So to convert between Celsius and Kelvins, you simply add 273.15 to your temperature, your Celsius temperature. In order to convert from kelvins to Celsius, you simply subtract 273.15 from your kelvins temperature. Here's a representation of the three temperature scales: Fahrenheit, Celsius, and Kelvin. Notice that at 100 degrees Celsius, we have the boiling point of water. And at that, on the Kelvin scale, it's 373.15, where it's 212 on the Fahrenheit scale. Let's take a look at these scales quickly, and we'll do some calculations in a moment. What is the temperature at which water freezes? Use these thermometers to help you. Zero degrees Celsius. Here we go. What is the temperature at which water boils? If we look here, we see that water boils at 373 kelvins. How many Celsius units are between the boiling points and freezing points of water? 100 degrees. Why is it that here we have 373 kelvins and not 373.15 kelvins? Well, looking at this temperature, looking at this thermometer, notice that our scale is not very tight, and we have to guesstimate quite a bit on this temperature scale, so we don't have any decimal places on the scale, and we should probably have an even less precise value shown here. To calculate the difference between Celsius and Fahrenheit, we use a different type of calculation. And because there is 180 Fahrenheit degrees that covers the same 100 Celsius degrees, looking at freezing point and boiling point of water, we use this calculation to help us convert between the two. Let's do a few calculations. A body temperature above 107 degrees Fahrenheit can be fatal. What does 107 degrees Fahrenheit correspond to on the Celsius scale? Remember, when we're solving problems, you always first want to find what is the known information. We've got 107 degrees Fahrenheit. Next, whether the answer is in units. We need to know the same temperature on the Celsius scale. Then we have to use our conversion factors. Well, in this instance, our conversion factor is an equation that we can use to convert between the two. When converting between Celsius, converting from Fahrenheit to Celsius, you need to, let's fix that right quick. I'm sorry, folks. I need to fix that right now. It won't, is it letting me? Okay, there we go. Sorry, folks. All right, you use the equation where we substitute in the known temperature in Fahrenheit, and in your calculator, you end up with 41.66666, and you round that to two significant figures to get 42 degrees Celsius. Let's try one on your own. Well, if we just look at this table here, we notice that body temperature is the same as 37 degrees Celsius. Doing the calculation, we see that 98.7 degrees divided by 1.8 gives us minus 32 gives us 37 degrees Celsius. Let me check something right quick, folks. Yes, that's correct. Okay, let's try another. Convert 37.6 degrees Celsius to Kelvin's degrees. Well, if we use the full value of Kelvin and we use our equation, we know that Celsius plus 273.15 gives us 300.75, which rounded off will give us 310.8. You know, we should round this off to actually 3 significant figures because we have here 37.6. So in actuality, this answer should be given as a 311 kelvins. I will fix this in the PowerPoint that I post on Blackboard. So, how do we measure units of energy? Well, we know that we use temperature to determine whether energy has been supplied or taken away. How do we know? Well, when temperature rises in a substance, what's happening? The kinetic energy of the molecules are increasing, which means that the heat is increasing, which gives us an increase in temperature. When we now have temperatures that are decreasing, we know that the kinetic energy of molecules is also decreasing. Well, that also represents a loss of energy and a loss of heat. So we use the joule and calories to determine measurements of heat. Now remember, heat can be lost or gained. If heat is gained, is it a positive or negative value? Correct, positive. If it's lost, it is what kind of value? Negative. In the US, we use the kilocalorie as our measurement of calories for our food on our packaging and food labels. It's actually equal to it's the big calorie with a capital C, and it's 1 kilocalorie, which actually is equal to 1,000 little c calories. Why do you think food labels in America have energy in big cows and not little cows? I think it might have something to do with scaring people if they really knew the amount of energy that they were consuming. And also, it's a shorter value to use, just like think of it as scientific notation, but it's not necessarily scientific notation. It's just an easier way to represent large numbers. So we can use these conversion factors between calories and joules. This is something that you should commit to memory. 1 calorie is 4.184 joules. It's simple to just remember it so that you don't have to go back and forth between your tables to find this information. And also 1 kilocalorie is equal to 4,184 joules. And we can use these conversion units to change between calories and joules. Let's try a problem. A defibrillator gives a high energy shock output of 360 joules. What is this quantity of energy in calories? Well, we're given 360 joules, and we need to know the number of calories. Our conversion unit is 1 calorie is equal to 4.184 joules. Notice that joules is a larger energy unit than a calorie. We set up our problem. 360 joules times 1 calorie divided by 4.184 joules. And if we put that in the calculator right quick, let's use our trusty calculator. Let's see, 360 divided by 4.184 0.04 joules gives us 86, gives us, what did our calculator say? Gives us 86.04 calories. Well, can we leave that as 86.04? Let's put that in the proper number of sig figs, and we will get how many sig figs do we need in total. If we're starting with 360, we only need 2 sig figs. So 886 calories. Does that make sense? It does make sense because joules is a much larger unit than calories, and we should have about 4 times as less calories than joules. All right, let's get back to the PowerPoint. Here are some other calculations to help you with converting between calories and joules. How many joules are in 5 calories? Start off what we were given. We use our conversion where we have joules on top, calories on the bottom, plug that into our calculator, and we get 21 joules. Let's try the next one. How many calories are in 25 joules? Start off with what we're given. 1 calorie divided by 4.184 joules. Notice that we put joules on the bottom, calories on top, and we end up with 6 calories. You try the next one on your own. Let's check to see if you're right. How many kilojoules are in 600 calories? Well, we set our conversion so that joules are on top and calories on the bottom. We plug that into our calculator. Oops, I forgot. This is going to kilojoules. So we have to use an additional conversion to convert our joules to kilojoules. Notice that we put our kilojoules on top and joules on the bottom, and we end up with 2.51 kilojoules when we put this in our calculator. What about 3.5 kilojoules to calories? Go ahead and try this one on your own. You can pause the video if you need more time to do your calculations. Start with what you're given, 3.5 kilojoules. We will convert now to joules from kilojoules. Notice we have joules on top and kilojoules on the bottom. And now we can convert from joules to calories. We cancel out kilojoules, we cancel out joules, and now we're left with calories for our answer. And rounded off to the correct number of significant figures, we have 837 calories. Notice for this problem we have a decimal place here, meaning that all 3 of these digits are significant, and our answer has 3 significant figures. We can use the energy that is absorbed or lost from a substance to calculate its specific heat. We also can use the specific heat of a substance to determine how much energy is lost or gained when the temperature changes of a substance. So let's think about it. Which one is going to absorb energy faster, a metal spoon or a wooden spoon? Have you ever left a metal spoon in a pot while something was boiling and then go back to touch it versus a wooden spoon? Well, if you haven't, don't really try because it might hurt. But think about it. The metal spoon, is much hotter than the wooden spoon. The specific heat of the metal is much lower, meaning that there's much less energy necessary to raise the temperature of the metal by 1 degree Celsius. So it is substances that have a higher specific heat that will take longer to heat up because more energy is required to warm that substance by 1 degree Celsius. So the specific heat of a substance has units that is going to represent everything in the whole system. So we have the amount of energy divided by the grams of the substance and the temperature change of the system. So we have two different specific heat units, one with joules and one with calories. And if we're looking at the specific heat of water, it's 1 calorie is needed to raise 1 gram of water by 1 degree Celsius. If we're looking at the joule scale, it takes 4.184 joules to raise 1 gram of water by 1 degree Celsius. So notice that the specific heat units encompasses the whole definition of specific heat. We can then use the specific heat to calculate temperature changes in a substance, and also we can use it to calculate initial and final temperatures. We can also use it to calculate the amount of substance if we're given the specific heat, and we can also use it to determine the amount of heat that is lost or gained from a substance. Here we have some specific heats of common substances. You can click on these links in the video, in this PowerPoint, on the PowerPoint that's posted on Blackboard, to watch videos that help you understand more about heat and specific heat and heat capacity. Notice that water has a much higher specific heat than any of these other substances. Notice gold gets hot pretty quick. It only requires a small amount. Mercury as well. So I was mentioning before that we can do all these calculations, and it's all because of the heat equation, where heat is equal to the mass of the substance in grams times the specific heat times the temperature change in Kelvin, in Celsius. So we have the mass times the temperature change times the specific heat. We can use calories or joules. And our heat, when we do our calculations and we cancel out all our units, we've got grams and degrees, and then we have our unit for specific heat, where we cancel out the grams and Celsius. Let's do a few problems. First, remember, you always have to think about what you're given, what you need, and what your conversion units are. So let's take a look at the first question. Taking a bath might use about 95 kilograms of water. How much energy in calories and joules is needed to heat the water from a cold 15 degrees Celsius to a warm 40 degrees Celsius? Let's think about this problem before we answer it. We want to know how much heat energy. Should our answer be positive or negative? Well, thinking about this, is the water being heated or is it cooled? The question is saying that it needs to be heated. So that means we have to supply an amount of energy. So our value that we get should be a positive value. Let's break down our problem and figure out what we need to solve it. Well, being that we're given masses and energies and temperature values, we have to know that we need to use our heat equation. We also know that we are given 95 kilograms of water, and we're also given that the temperature, our initial temperature is 15 degrees, and our final temperature is 40 degrees. We also know that C in our equation, since we're talking about water, our specific heat for water is either 1 calorie or 4.184 joules per gram. Let's go back to our problem. All right. So we know that the specific heat for water is 1 calorie per gram degree Celsius, or 4.184 joules per gram degree Celsius. In this problem, I'm going to calculate calories and then convert to joules. You can do either way. Or you can calculate both of them using the same method I'm going to use here. We know that we're given 95 kilograms, but for our equation, everything needs to be in grams. Notice our units for specific heat. So if we convert kilograms, we get 9,500 grams. We know that our initial temperature is 15 degrees, the final temperature is 40 degrees, and we need the amount of heat. So setting up our equation, we know that Q is equal to mc delta T. Plugging in everything, we cancel out grams, cancel out Celsius, and we end up with 2.4 times 10 to the 5 calories. If you plug it in your calculator, you'll get another number, but know that we have to round it off to two significant figures, and scientific notation is much easier for these large numbers. If we want to calculate the joules from this, we simply use the conversion factor that 4.184 joules is equal to 1 calorie. If we just plug in 2.4 times 4.184 in our calculator, we end up with this number. Just simply bring down your exponents here, and then we can just change and put it into proper scientific notation. 1.0 times 10 to the 6 joules. Let's go ahead and take a look at another problem. We need to know how many kilojoules are lost when 5,500 milliliters of blood is cooled from 38.5 to 33.2 degrees Celsius. We're going to assume for this problem that the specific heat and density of blood is the same for water. So we need a couple of conversions in this problem. So the question is asking, what is the amount of energy that is lost? So if energy is lost, should our energy value be negative or positive? Well, when we lose energy, we end up having a negative value. So when we do our problem, we should be looking to have a negative energy value. That negative value simply means that energy is lost. There is no negative heat. However, the negative sign just simply lets us know that heat is lost. So we need to use the specific heat and the density of blood as our conversions. Note that we're given 5,500 milliliters. However, in our heat equation, we need mass. So we use our density of 1 gram per milliliter to determine that we have also 5,500 grams. We know that our initial temperature is 38.5 degrees and our final temperature is 33.2 degrees. Setting up our delta T, we see that T final is a negative 5.3 degrees. We need to know our value of Q in kilojoules, so we'll have to do another conversion in the end. All right, so let's set up our equation. We're plugging and chugging. Our mass is 5,500 grams times our specific heat in joules, because the question is asking for kilojoules. That's 4.184 joules per gram degree Celsius times minus 5.3 degrees Celsius. We also need to have our answer in kilojoules, so we need to convert joules to kilojoules. We have our conversion here. Plug everything in your calculator and you get 122 kilojoules, noting that we have to have you know what? We need to have two significant figures, so the answer should be, instead of 122, should be what? Correct, 120 kilojoules. I'll fix that before I post again. before I post this to Blackboard. One more problem. If 55 grams of olive oil has 877 calories of heat added to it at a room temperature of 26.0 degrees Celsius, what will be the final temperature of the olive oil? The specific heat of olive oil is 2.19 calories per gram degree Celsius. So this question is asking us to find the final temperature. What do we have? We're given 55 grams. We have 877 calories of heat. And the initial temperature is 26.8 degrees. After we add the 877 calories of heat. We're going to use our specific heat as in our problem because we need to use the heat equation. So we know we're given 55.5 grams. We know that the energy is 877.6 calories, which is supplied to the system. So that is a positive value. So our final temperature, should it be greater or less than what we have now? Right, it should be greater than because we're supplying a certain amount of energy. So we know our initial temperature is 26 degrees and we need to find our final temperature. We have to do a little bit of manipulation of our heat equation to find out what T final is. Well, we've got the mass, we've got C and delta T. Well, if we remember, delta T is T final minus T initial. Rearranging our equation, we have Q divided by MC is going to give us T final minus initial. Here we go with another mistake, y'all. Let's fix that. So here, being that T initial, is it going to let me? That should be plus. Oh, come on, let me type in here. Let's insert a text box, and I'm gonna put it right here, and I'm gonna type times. No, not times. Plus. And let's make that guy bigger. Let's do that here. And here we're going to make that a plus. Let's delete U. And let's copy this guy. Let's copy him here. And here. Can we remove him? Yes, we're going to remove him and put another plus sign here. And we are going to fix our answer by deleting this. And let's take a look. So when I did my problem, I did not check to make sure that my answer was correct. Let's plug this into our trusty calculator over here. Let's clear them out. 7.3 plus 26. It's going to give us 33.3 degrees. Let's stretch this out. 33.3 degrees. Let's copy this little dude. Oh no, I can't copy him. Oh, can I copy? Well, you guys get it. It's 33.3 degrees Celsius. Let's see, symbol. I know, I'm sorry, folks. And I did go over this. 33 degrees, capital C, Celsius. Okay? All right, let's get back to the presentation. How about you do a problem on your own? Water has a specific heat of 4.184 joules per gram degree Celsius. How many kilojoules of energy are required to raise the temperature of 0.453 grams of water from 21 to 37 degrees Celsius. You can pause the video if you need more time to do your calculations. The answer is 30.3 kilojoules. First, we know that we need our heat equation. We're given for 0.453 kilograms, which we need to convert to grams for our equation, which is 453 grams. We know that our initial temperature is 21 degrees, our final temperature is 37 degrees, so that we need to have a positive or negative value for the heat. Well, it said that the temperature is raised, so that means that we need to supply amount of heat, so our value for Q should be positive. We plug in everything, we plug in all of our values, and we end up with 30,326 joules. We need to convert that to kilojoules, and we get three significant figures, 30.3 kilojoules of energy. Notice it's a positive value. Last, we're going to discuss density. The learning objective here is to define density in specific gravity and use these quantities in mass volume calculations. Well, we know that density is a physical property, and it tells us the amount of stuff that there is in a certain volume. So it's the amount of mass per unit volume. And we know that things that are more dense have more mass per unit volume. So let's say a cotton ball the size of a golf ball is going to be less dense than the golf ball because there's way more stuff packed into the same volume in a golf ball than there is in a cotton ball. So what are the units of density? We can have grams per centimeter cubed or grams per milliliter. Note that we can convert easily between milliliters and centimeters cubed. The density of a gas is going to be grams per liter. Being that a milliliter is such a small amount, that we don't have gram amounts of gases in a milliliter. We can determine the density of a solid by using the displacement method. If we have a known volume of a liquid and we place a solid in there, we can see our initial volume and our final volume. The difference between the two is the actual volume of the solid. Therefore, once we have the mass of the solid that we can take here on analytical balance, we can find the density by putting 68.60 grams over 9.5 milliliters. We got that from the displacement method. We end up with 7.2 grams per milliliters. Knowing that we can convert milliliters, it's best to use centimeters cubed for a solid because we don't have milliliters of solids. That's a milliliter of a liquid. So we just simply convert milliliters to centimeters cubed. Now that we have the density of a substance, we can use this value if we're given the mass to determine the volume, or if given the volume, we can determine the mass. Here we have some densities of common solids or common substances. Notice that most substances, you don't see it here, not on this table, but water has a density of 1 for liquid, yet the density of solid water is slightly less than that, and it floats on water, which is why we have ice water. And the reason that this is so important, especially to human life, is that if we didn't have ice that covered oceans in very cold regions of the earth, life wouldn't be able to live in such cold water. The ice helps to insulate the ocean beneath. What are some other substances that you know can float or sink in water? Here we have a density column where it's representing the different densities of different substances. You can click on these videos in the PowerPoint listed in the PowerPoint posted on Blackboard to help you understand density and to get more density practice. Let's do a couple of problems together. What volume of isopropyl alcohol would you use if you needed 25 grams? Given that the density of isopropyl alcohol is 0.7855 grams per milliliters at 20 degrees Celsius. Well, we need 25 grams, but we also need to know what that volume is. We can use the density as a conversion factor. Given that we have 25 grams and the density is 0.7855 grams per milliliter, we need to know the volume. We know that density is mass divided by volume, but we need to rearrange this equation so that we get volume by itself. Multiplying both sides by the volume, we get dV equals m. Now we have to divide both sides by the density to get volume is mass over density. Plug in all of the values, 25 grams divided by 0.7855 grams per milliliter. Crossing out grams, milliliters now comes to the top, and we end up with 31.8 milliliters. How about you try the next one on your own? During surgery, a patient receives 3.0 pints of blood. How many kilograms of blood with a density of 1.06 grams per mil were needed for the transfusion? Don't forget, you're going to need a conversion unit from pints to milliliters. You can go back in the PowerPoint and find the table where we have the conversions between metric and English conversions. Take a moment to solve the problem on your own. If you need more time, you can pause the video to give you more time to solve the problem. First, we've got 3 pints of blood, and we need to know how many kilograms of blood that is, given the density. However, our density is given in grams per milliliter, and we need to know our value in kilograms. So first, we can figure out that if we divide our density, both sides of this equation by the volume, we end up with mass is equal to dV. First, we have to convert our pints to milliliters because our density is given in grams per milliliters, so we have to have our volume in milliliters. If we go back to our previous slide, we know that 473 milliliters is equal to 1 pint. Putting all that into your calculator and rounding it off to the correct number of sig figs, we get 1400 milliliters. Now, plugging that into our rearranged density equation and also using our conversion of kilograms from grams to kilograms, we end up with 1.5 kilograms of blood. Alternately, we could have left this number with an extra number of sig figs so that we would have a more precise answer at the end of our calculations. Let's do a couple more of these density calculations. What is the volume of a gold nugget that weighs 2.2 kilograms? Given the density of gold is 19 grams centimeters per centimeters cubed. You can pause the video if you need more time to solve the problem. We're given that we have 2.2 kilograms, which we need to convert to grams because our density is given in grams per centimeters cubed, and we know that our density is 19 grams per centimeter cubed. We need to know our volume in centimeters cubed because that's what our density is, and we're looking at a volume of gold, not a volume of liquid gold, since it's a nugget. So converting our density equation, we get volume is equal to mass over density. Putting in our values of 2200 grams divided by 19 grams per centimeter cubed, canceling out grams, we get 115 centimeters cubed. However, our density, well, I guess we can leave our answer as 115 centimeters cubed. We'll leave it at that. Because, well, no, we can't, because the density is given in 2 sig figs, so our answer has to be given in 2 sig figs. 120 centimeters cubed. How many liters of fat would have to be removed to result in 4 grams of weight loss when the density of human fat is 0.94 grams per milliliter? Why do humans float in a pool? If you have more body fat, why is it easier for you to float than it is for someone with less body fat? Could it be that human body fat has a density that's less than water? Anyway, back to the problem. We're given 4 pounds, but our density is in grams, so we need to convert that 4 pounds to grams. We know that 1 kilogram is 2.20 pounds, and we need to convert that kilograms to grams. And we get 1,818 pounds. 18 grams. We have the density that's 0.94 grams per milliliter. So now we need our volume in liters. Okay, our rearranged density gives us the volume is equal to mass over density. Put in those values, 1,800 grams divided by 0.94 grams per milliliter, and we end up with 1,914 milliliters. We need to have our value in liters, however, so we need to convert from milliliters to liters, and we have 1.9 liters of fat. Just to lose 4 pounds. So let's say you go to get lipo and they remove 4 pounds from your belly. That would end up being almost 2 liters. You know what a 2-liter water bottle looks like? Or if you look at one of those, the IV bags, that's like a liter. The big ones were for saline solution. 2 of those would have to be removed. Almost 2 of those would have to be removed in order to get rid of 4 pounds of fat. Interesting, huh? Oh man, I already gave you the answer to this one. Mercury has a density of 13.6 grams per mil. How many milliliters of mercury have a mass of 475 grams? Being that the answer is already given to you, we'll go ahead and solve the problem. We've got 475 grams. We need to know how many milliliters. Our density is mass over volume. Rearranging our equation to find the volume, we get mass over density is 475 grams divided by 13.6. Plug it all into your calculator, cancel out grams, and you get 34.9 milliliters. Specific gravity is the density of a substance divided by the density of water at the same temperature. So let's say the specific gravity of urine, if it is equal to 1, then its density is the same as water at that temperature. So at normal temperature, the density of water is very close to 1, and at normal temperature, the specific gravity of a substance is actually equal to its density. So, and that's because water is 1. So the specific gravity of a liquid can be measured using an instrument called a hydrometer. And we use these in medicine to determine the amount of solids dissolved in urine. We won't be doing any of these calculations on exams, although you have done some in your learning modules. That completes the chapter 1.1 part 3 PowerPoint.